This is a presentation on persistent disk, or as we affectionately call it, PD. My name is Jay Judkowitz. I'm a product manager for PD. This is Andrew Kadatch, our tech lead. And it's a 30-minute presentation where we'll go through what persistent disk is, what we use it for, how it works, what are some of the main beneficial properties to you as developers. And then we're going to spend most of our time, actually, Andrew, talking about the best practices, how you get the most out of it, how you protect it, how you get some advanced use out of it. And then we'll try to save 10 minutes at the end for Q&A. So let's jump right into it. So the first thing we like to say when we talk about persistent disk is talk about the context of the rest of cloud storage. A lot of our cloud storage offerings are actually managed data, whether it's a blob or a NoSQL database with data store, or Cloud SQL, which is kind of a MySQL implementation, or BigQuery. But every now and then you don't want managed data. Every now and then you want to manage the data yourself, and you need raw block devices. So Google has two block devices for this purpose. One is the scratch devices, which we used to call ephemeral disk. Those live and die with VMs. A VM's created, you get the scratch disk, and then when you kill the VM, scratch disk goes away. Persistent disk is, well, persistent. You create it independently of a virtual machine, mount it and unmount it from a virtual machine as you need, and can mount it to a new VM if a first VM dies. Basically, persistent disk is a cloud-wide SAN for your use. Three primary use cases for persistent disk. First is as a boot device. So you can boot off of a persistent disk if you have a stateful application, one that you need its configuration to survive after you shut it down and turn it on many times. The more common use case right now is as a data drive. So regardless of whether you're booting off of scratch or persistent disk, if you're running a data store like HDFS file system for Hadoop, if you're running an NFS server, a MySQL database, a NoSQL database like a Mongo or a Cassandra, having a persistent disk as a data drive is the way to keep that data living across instantiations of that database. And obviously to keep it highly available so you never lose that data. The last use case is actually really unique to Google. And let me start with the use case here. Imagine you're some scientific computing application developer, or you're doing some sort of render farm, and you have data that you create once, but then need it available to many workers. Many workers are going to compute on this genomic data or on this image. So persistent disk gives you an option as opposed to copying it everywhere. Instead of copying it to every worker, you can just mount the persistent disk to very large numbers of virtual machines, and they'll have instant access to it. So this can scale to at least hundreds of VMs. So before I get into how persistent disk works, we'll talk about one of our partners who's had a lot of success with persistent disk and their customers. People are probably pretty aware of MapR. They're a Hadoop distributor. And they basically use the first two use cases of persistent disk. They encourage their customers to use it as a boot drive always because they want the Hadoop cluster configuration to survive death and restart of instances. And then they also will suggest some of their customers use it as the data disks. The MapRFS can, if you lose a scratch disk, let's say, can replicate the data. But if you lose the entire cluster and bring it back up, you would have to re-import the data. So if you're going to shut down and restart entire Hadoop clusters, it's better to use persistent disk on the back end. Now, the concern that they had going into it was performance. In other clouds, people say, oh, you have to use ephemeral disk for something like Hadoop. They were very pleasantly surprised. They found that persistent disk performed about as fast as ephemeral disk in other clouds. And they were able to consistently get 120 megabytes per second through the persistent disk using their application and how they tuned it. So let's talk a little bit about how persistent disk works so we can get to why some of those benefits exist. So the first thing to note is that a persistent disk is not actually a real disk. It's a virtual volume that is made up of blocks from many, many underlying physical devices. And so one block is cut up and striped and smeared across many, many, it could be hundreds or thousands of physical devices. Now, each of those blocks is encrypted, which is critical because I'm sure we've talked about security in a lot of the other sessions. You want to make sure there's absolutely no circumstances where somebody else can get to your data. On top of the security, we also do checksumming. When you retrieve data that you've stored, you want to make sure that it's exactly the data that you had. So we take care of this all underneath the covers. We will not return bad data to you ever. Now, let's talk about what we do with that data for performance. So the first thing is, we're going to optimize for random writes by basically writing anywhere in the cloud that we feel is a good fit for that block at that time. So this is going to help you. Let's use a database use case. If you're doing a lot of transactions that are randomly writing all across your database, you don't know who the user is going to come in, what transaction they're going to do, or where in the database they need to write to. You want to know that every write is going to go to a good part of the cloud that isn't affected by a noisy neighbor and gets you consistent write performance, even with randomness. And then moving over to reads, what you'll notice about these copies that's interesting is it's not an active passive copy. Each one of those copies can actively take reads. So we will get a read from the first guy that responds. We'll put out the read everywhere. Whoever comes back first wins. Again, this is going to add to consistency of performance. So now if you're trying to figure out, oh, how much data and how much I/O do I put to a particular data volume before I create a new database shard, that doesn't become an exercise in randomness. That actually is, you could apply a very specific formula to that based on your workload. Now moving away from data volumes back to a boot volume use case, what we do is, again, we can boot from PD. The PD is striped and spread out across lots of volumes. But what happens when we create another copy of the VM that has high commonality with the previous one? Well, very, very soon, it's not released this moment, but very soon, we'll basically be able to create a new copy with basically virtually referencing the previously copied blocks so that you get an extremely fast deploy time. And the idea, so like, when you guys saw Urs's talk this morning and Greg's demo, the idea that you could do like 1,000 VMs in 5 minutes, right? We could do that, and we're looking to get even faster. And of course, even though they're reading off of shared blocks, we're not going to corrupt it. If you add a block to one or change a block on another, that's going to be a new write elsewhere in the persistent disk cloud and not going to corrupt the shared blocks. This slide gets to another extremely unique feature of Google Cloud, but it's not persistent disk only. It's in teaming up with Google Cloud Storage, or GCS, or blob storage. So the common thing that everybody knows about is if I want to be able to copy data to another site, whether it's for VM migration, backup, disaster recovery, I can snapshot my block device into blob store. A lot of other clouds have the ability to do differential snapshots, so I only have to copy the changes. This is something we'll be coming out with very soon as well. But what's really cool is that GCS cloud, you notice I didn't put that in one of the data centers when I made the slide. That's actually globally available to all data centers simultaneously. As soon as you get that confirmed back on that write, you're able to use that snapshot somewhere else. So now I can, here take the snapshot that I made from the central region in the US and deploy it in Western Europe immediately after I get the ACK. So a couple quick notes on using persistent disk. I'm going to talk very briefly about the things that are kind of obvious and well documented, try to spend a little bit of time on things that are not 100% obvious, but then I want to hand it over to Andrew to talk about best practices, because I think that's why a lot of people are here. So the first thing is we have a REST interface for programmatic use of the product, and we have a command line and UI for more administrative use. And the commands are what you'd expect them to be. Create volume, delete volume, mount volume, unmount volume. It's all well documented, and everybody can see that. So what does the volume look like inside the virtual machine? The first thing to note is that it shows up as a VirtIO SCSI device, and it shows up with a symbolic link to a device so you can easily find it. Basically, the name that you created it with will show up in the device model inside the VM, which will help you find it for mounting. We do give you a command for formatting and mounting the volume, which is actually pretty useful. Andrew will talk about why we created that. Talks basically about block alignment and performance assurance. Now, if you want to make sure that every time you create a virtual machine, a persistent disk is mounted into it, a couple ways you can do that. First, if you're booting from PD, obviously you edit the FS tab for any of the data volumes you want to boot and you want to mount, and that'll always mount properly the next time. If you're booting from a scratch disk, though, you lose the FS tab every time. So you can use the custom startup scripts and the custom metadata variables to basically script your way around making sure the data drive mounts every time. I did have some sample code on that, but everybody was embarrassed of the PM shell scripting, so it's in backup slides. Like any system, PD has limits. Limits are, like Urs mentioned this morning, and I think like Navneet mentioned in the GCE talk today, we've increased that depending on the size of the VM previously. It was anywhere from 128 gig to 1 terabyte volume limits. Now we've radically increased that. You can create 3 terabyte volumes on the very small VMs, the sub-core VMs, and up to 10 terabyte volumes on the previous size VMs. And the number of devices, 4 for the small VMs, 10 for the bigger VMs, it's not 10 times 10 terabytes for 100 terabytes. It's 10 volumes adding up to 100 terabytes. Sorry, 10 volumes adding to 10 terabytes is the limit. And so that should really take care of pretty much any size needs I think people have, and compares I think very favorably to other clouds. Now, to ensure the consistent performance, one of the things we had to do was limit the I/O rates. So for large I/O blocks, you'll hit a bandwidth limit of somewhere around 120 megabytes, and for smaller I/Os, you'll hit read I/O limitations. Now, if you want to get more smaller I/Os, you can add multiple volumes to a VM and stripe them together, and Andrew will show some data on that in the best practices session. And again, the 120 megabytes is pretty good for a best effort volume, right, as the MapR guys found and we talked about in the previous slide. Now, in terms of pricing, the price is publicly listed. What's good about this is, like GCE, the billing increment is now very small. So even though the price is per month, when you create the virtual disk, you don't get charged for a whole month. You only get charged for the time that it lives. And that increment is something under 5 minutes. If you want to see what your price is at any given time, how much you've accrued over the course of a month, you could go to the Cloud Console and check that out. One of the things to note is the Cloud Console does update its display on a daily basis, but you're not actually getting charged on a daily basis. It's still accruing in very small increments. So don't panic when you see that happen. So that's kind of the overview of what PD is, what it's good for, and a little bit of how it works. And let me hand it over to Andrew for how you guys can get the most out of it.
Thank you. Thanks, Jay. When we started working on Persistent Disk a while ago, we put a couple of goals ahead of us. And the first and most important one is durability. If we lose data on the left and on the right, everything else doesn't matter. Simple. Second goal was security. If I cannot trust my cloud provider with my data, I'm not going to use it. So everything else doesn't matter either. Getting back to durability. So we replicate the data and we provide sufficient mean time to data loss to say that persistent disk's mean time to data loss exceeds mean time to data loss of typical enterprise class SATA disk by 1 to 2 orders of magnitude. Security, what we do, we encrypt the data, and we encrypt it not only at rest, but over the wire too. So it's extremely difficult to get to the data. And to be honest, I myself don't have access to encryption keys. So we made it as hard as possible for ourselves. High availability. I should be able to get the data when I most need it. Typically Tuesday morning at the peak traffic in cloud services. And if I cannot get it, my disk is unusable. Typically, we are able to achieve variability in I/O execution latency within 3%. The more cores VM has and the smaller the bandwidth, the better variability, the better availability and consistency is. And the same applies to consistency. If it's closely related to availability, the thing about consistency is that it's extremely important for capacity planning. Should I be running 2 instances of my SQL services or 20 to meet my peak demand? I need to know upfront, and I need to plan accordingly. And finally, performance. We bravely wanted to meet or exceed performance of locally attached SATA disk. Obviously, mission impossible because of encryption, network latency, replication. It was not, but I think overall for many services we achieved pretty good performance, and it's suitable for the use. However, before we will talk about specifics of persistent disk, let me take a step back and say that one lesson that we all learn at Google every day is simple. The luck favors the prepared. It was said by Louis Pasteur, and he knew exactly what he was doing. So the problem is that disasters do happen. Human mistakes, software bugs, natural disasters happen all the time, and we need to be prepared. The way to get prepared with persistent disk is using snapshots. Snapshots are a very efficient way to implement backup and restore. The data is geo-distributed, snapshots are non-intrusive, they are extremely efficient, and most importantly, they do not affect performance of the volume, so you can take it any time. So I would strongly urge, and probably I will repeat it multiple times, to automate the process, test it regularly, and have regular snapshots. What I would do, I would make snapshots, say, hourly, keep a couple of days of hourly snapshots, then I will remove all snapshots and have a couple of daily snapshots, few weekly, and a handful of monthly just in case, because sometimes we don't notice the problem right away. Sometimes it takes time to discover it, and I should be able to get back in time and restore my database or my data set to correct state with minimal data loss. One thing is extremely important. We really have to use journaling file system when we use persistent disk, because file systems cache a lot of internal data structures in memory, and if those data structures in memory are not preserved on the disk, in case of undesirable event, we will have massive data loss. And from our experiments, when we used non-journaling file systems and simulated various failures, under heavy I/O load, we were able to cause massive data losses or irrecoverable file system corruptions in 40–60% of cases. It is very substantial. Please use journaling file systems. Making snapshots is really easy. The safe way to do it is to freeze application data file and file system, make a snapshot. Making a snapshot is two-phase operation. One is making a snapshot, effectively taking instantaneous photograph of volume state, and then copying the data out. When we start copying the data out, snapshot state changes to uploading, and when we finish copying, it becomes ready. So the moment snapshot state converts to uploading, it is safe to release and unfreeze application and file system. Two caveats. First of all, we need to separate application data and operating system. You cannot freeze OS partition or volume. So it's simple as that. Secondly, for some applications and some file systems, it may be not necessary. For instance, if we run a SQL server which supports transactions, and we run a journaling file system, if you just make a snapshot while everything is running and restore another VM from the snapshot, it will look as if there was a power failure at the moment snapshot was taken. File system will recover from that. SQL server will recover from that. The problem is that it may take time. And it is different trade-off. Sometimes it's beneficial to freeze and take a snapshot. Sometimes it's OK to keep going. Today, Google implements 2-week maintenance windows every quarter per cell. And I see it as a wonderful opportunity to make sure that your recovery and scripts are working and doing the right thing. As a developer, when I joined Google, I really hated that. Now I really love it. It is a nice forcing function to ensure that we are doing the right thing and our products work and are ready to face the disasters, because they will happen. And I would strongly recommend visiting the next session we will have on Friday at 2 p.m. in room number 2 by Mark and Joe, where we will talk about it a little bit more. And we provide some tools to simplify the migration of your data and VMs to another cell or zone using gcutil move instances command that will make it fast and efficient. Or if you prefer, you could use your own scripts. Amateurs backup, professionals restore. Please, please, please automate everything you can. Take snapshots regularly, test your recovery routines, and make sure that it works. The luck favors the prepared. Now, let us proceed to persistent disk PC. In many environments, it is nice, well-known trick to create a lot of volumes, test their performance, and pick the one that works the best and throw away the rest. It is not necessary to do with persistent disk for a variety of reasons. We decide actual data placement at time of write, so the past performance doesn't matter. We deal exceptionally well with noisy neighbors. I would say about in 98% of cases, if there is interference at physical disk level, we resolve it within from 2 to 20 milliseconds, so it's extremely efficient. So I just took the data from last 10 automated performance runs that we run all the time. Unfortunately, it's a very boring slide. There was much, much, much less than 1% variability between runs. Similarly, there is no need to pre-warm the volume before use, filling it with data, doing full format, etc. The volume is ready to use and go from the day one. That is 2-hour run, and those 2 horizontal lines represent average I/O execution latency and bandwidth respectively. And to make the stuff a little bit more interesting, we threw a curvy ball. That wavy line represents the latency of the slowest I/O during 1 second period. And as we see at one case, about 30 minutes through the run, it took about 3.5 times slower than average, which is not too bad. There was exactly one I/O which did that. Finally, we have something interesting. 3 classic textbook scalability graphs. What happens if we stripe volumes, which is yet another well-known trick to improve performance? Yes, performance will improve. On small random writes, we scale really well and max out at about 6 volumes. On small random reads, we scale practically linearly. With large sequential writes, which simulate bulk data processing workload, we max out, and then performance drops because those volumes starts to compete with each other at process level network. But what I would like to say, you can do that. Nobody can stop you. I would strongly discourage from doing that, because I don't like the need to do something awkward and extraordinary to get what you should be getting. We will change that. You will get a way to get good performance without the need to go to extreme measures. That's problem number 1. Problem number 2, whenever you stripe volumes, reliability of the volume, mean time to data loss, drops dramatically. And because we have absolutely no control of what's going under the hood, unlike persistent disk where we have a lot of control and we already stripe it under the hood, you will have degraded durability of the volume. Third, it is extremely difficult to take consistent snapshots of multiple volumes. It is difficult and error-prone to maintain those snapshots in time. So if you have to, do it. Otherwise, I would suggest avoiding doing it. Performance of persistent disk, throughput, latency, well, mostly throughput and number of IOs per second, depend on IO size and number of IOs in flight. The more IOs in flight we have, the better the performance. The larger IOs, the better the throughput. And as we could see from those graphs, it is especially noticeable on small IO blocks. And we recommend to use block size multiple of 4 kilobytes. And I will talk about that a little bit later. The thing is that persistent disk internally is implemented as a physical device with 4 kilobyte physical block and 512 byte logical block size. It means that the minimal unit of physical access to the data is 4 kilobyte, which means that if, for instance, we are writing one sector, 512 bytes, what will happen under the hood? We will read entire 4 kilobyte block, modify small part of it, and write it back. Read, modify, write cycle is slow. And actually, a lot of people who are using modern hard disk notice that because they have 4 kilobyte physical blocks too. Another thing that may happen, even if we are doing sequential I/O, if it's misaligned, we will generate not only read, modify, write cycles, but we will get overlapping IOs because each IO will be extended to nearest 4 kilobyte boundary, and then they will start to overlap, and then they will be serialized, so they don't corrupt each other's data. It is very slow. Please avoid doing that. Typical mistakes that people make is partitioning their disks. First of all, I would strongly discourage doing that until you absolutely have to do it. There is no need to take a large persistent disk and partition it into multiple subdisks. It's better to just create multiple disks. Secondly, I would recommend using modern tools like fdisk, one of the latest generation, who do the right things to partition if you have to. And third thing, once you're done partitioning a disk, please double check that everything is right by running fdisk-lu command. And if you see that line in red, the partition is misaligned. And if partition is misaligned, all IOs to that partition will be misaligned and will be extremely slow. So that red line, it's not something that I typed on the slide. It's output from the command, so it's easy to grab. So when we talk about file system formatting, I would recommend aligning partitions on 1 megabyte boundary. It's default setting for modern fdisk, for latest versions of fdisk. I wouldn't recommend modifying that. I would recommend formatting the disks with 4 kilobyte blocks, use journaling file system, and we provide instructions and utilities how to do that correctly. Another thing to talk about is how we could use persistent disk to efficiently distribute data. Well, as Jay mentioned, mounting persistent disk read-only is a very efficient way to distribute data within the same zone. What we could also do, we could take a snapshot of the disk and then recreate a disk in another zone and mount it read-only to another large set of VMs, and kaboom, within few minutes, we distributed very large data set across hundreds of machines. When we mount persistent disk read-only, I recommend you measure the performance because actual performance varies and depends on the workload a lot. We handle edge cases extremely well, but something in the middle may vary. If we may scale from few hundreds, from low hundreds to low thousands, but you need to measure on your specific workload, on your specific scenario. Importing data from PD, if you have data sources somewhere else, is relatively easy. We could use SCP or gcutil push command to move the data from your data warehouse to persistent disk. From other storages like block storages, object storages, we can use tools provided with them. And for demanding applications, for accelerated data copying, transferring huge quantities of data, you may want to look at third-party providers like Aspera, who do that reliably and efficiently.
Well, thank you, Andrew. So I noticed you got an ovation, clapping when you finished, but not me. So thanks for joining. We're going to go to Q&A in a second here, but just to summarize. First, we talked about how performance is optimized for storing large persistent data for databases, whether it's SQL or NoSQL. We get rid of noisy neighbor problems, whether it be on reads or writes, by distributing the data, writing to free disks, and reading from whoever is available most quickly. Besides scaling on data access, we scale on the boot devices by deploying extremely quickly and using shared blocks wherever we can, so we can handle those burst use cases like Greg was talking about this morning. And again, all these services are better together. Using GCS for your backups and your DR gets data off-site super fast, and then also is able to give you more scale. Again, this massive read-only mount use case we talked about for scientific computing or rendering or other things like that. And lastly, hopefully it wasn't too scary, but we did give you a lot of best practices, a lot of ways to keep your data safe and to keep it working very fast. So follow the best practices that Andrew shared with you. The slides are available, so you don't have to remember it all. And I guess let's turn it over to questions. Thank you very much for joining.
So we're running various Hadoop clusters today, currently on AWS, and we use instant storage, which is like not very satisfactory because they're quite small volumes, as you probably know. So two questions really. One is, it sounds like you're saying that you could use PDs as disks for HDFS data nodes, and the I/O is probably good enough, or comparable with instance storage. Is that what you say?
So what the MapR guys found, I haven't used this personally, but the MapR guys basically said, if you use the Scratch disk from Google, it will perform better. I mean, they basically took, when they optimized the MapRFS, similar to how HDFS was done, it was optimized for locally attached SATA devices. Now, they just found some of their customers couldn't use that because they were going to shut down the whole cluster instead of one VM at a time. And what they found was, PD was actually fast enough. They thought it wasn't going to be based on experience with other clouds. So I'm not going to say it was, in that use case, as fast as Scratch. But they were able to stream 120 megabytes to a volume. And if that's good enough for you, and if you value the flexibility of being able to shut down the cluster more than the raw performance, then it's a good option. It's just a flexibility versus performance trade-off. But you're going to do pretty good either way.
That third use case you talked about, the parallel read use case, actually that's my preferred option because actually realistically I'd rather just be able to shut down the whole cluster and bring it up instantaneously. And if I've got HDFS running, it's hard to do that. So are there any limitations to that parallel read in terms of the number of instances and the combined throughput you could have across all of those?
So like Andrew was saying, it is going to be a little bit dependent on the workload. If you think about how we architected it, where all the data from a particular volume is striped out across thousands of disks, if you mount it to a lot of VMs, and each of those VMs are accessing different parts of the disk, you're actually going to get additive performance. I mean, it's going to perform like, it's going to seem to defy the laws of physics because you're going to have hundreds of VMs accessing hundreds of blocks on hundreds of physical devices over hundreds of NICs. Now, let's say you have the opposite case, where somehow you synchronized it so that every VM reads from the same block at the same exact moment. We're smart enough not to go to disk each time on that, but you're going to throttle the network card on the few machines that are holding onto that block. So it's going to depend on your workload. The more random the access, the more linear that thing's going to scale.
All right, thanks.
Hi there. Very briefly, you'd mentioned that it behaves very, very well with ext3 and ext4. Have any of the other funkier file systems been tried with any degree of success?
Is funky a technical term?
I believe so, yes.
Okay.
Excuse me, I didn't hear the question.
Yes, besides the ext3 and the ext4, are there other file systems we've played with?
ZFS, something along those lines.
Yes, we played with other file systems. We liked performance of ext4 in our tests, aggregate workloads, aggregate performance across a variety of workloads that we tried on, which is by no means representative or matching your specific needs. It did the best overall.
Very good, thank you.
Other questions? We still have 5 more minutes. I'll have them lock the doors and make you ask questions.
Can I ask a quick question?
Okay, absolutely.
So if you get to the point where you need a big chunk of it to come down, is there best practices for downloading from the persistent?
I apologize. You're actually way taller than the mic. Can you?
I was just wondering if you get to the point where you actually want to retrieve the data, is there best practices for being able to download it efficiently to your some local system?
There are multiple ways to do it, and I think what I will say applies to most cloud storages. Like SCP copy, using similar means you copy the data to another machine, or you could copy it to cloud object storage. For instance, Google Cloud Storage, and get your data available from anywhere. So there are a variety of ways to accomplish that.
Right, so just the cloud storage in particular, if you're uploading to cloud storage, you can use the parallelism and the object composition to get stuff up quickly. In terms of downloading from Google Cloud Storage, you have the ability to, you have the, what are the things in terms of download we can do? GCS.
I would.
Yeah.
I would say,
GSUtil
Yeah.
is optimized for getting as much data down as quickly as possible. And they are, yeah, sorry.
Go ahead.
How do you guys manage your encryption keys, and can I supply my own custom ones?
May I ask you to talk to the microphone?
How do we manage the encryption keys?
There is a service which owns those keys, and they are passed to the VM. VM itself cannot query those keys or ask to give it to it. If you know top layer, management layer, which is trusted one, and runs on separate machines and under separate accounts, if it believes that this VM should be able to mount the disk, it gives it a command to do so and passes the keys. Nobody else is able to access those keys. We restrict the access, and it's audited, et cetera, et cetera.
All right, well, thank you all very much again. I hope you enjoy the rest of the show. Thanks for your time. And if you have any follow-up stuff, anything you want to talk about in terms of feedback, feature requests, anything, do feel free to reach out to Andrew and I directly or the mailing list on the last slide.
Thank you.